Okay, good morning, all of you. This one is the fourth unit of your syllabus VLSI system design. है ना? आज का जो हमारा टॉपिक है, today's topic is system design. Today's topic is system design. This one is the fourth unit of your VLSI system design subject. Before starting this topic, that is subsystem design, first we have to know that what is the mean of subsystem. Okay, this topic we discussed on the basis of designer's point of view. Suppose I am a designer and I want to design any system. Suppose I am a designer and I want to design a system for some third person or for a third party. Then first I divide my system. First I divide my system on various subparts. So the subpart of any system is known as subsystem. Subpart of any system is known as subsystem. Suppose this one is the processor. Suppose this one is the processor P that I want to design. So before starting, I think I have to design this whole system. So I divide this system into various small systems. I divide this system into various subpart. I divide this system into various subpart. So these subparts are known as subsystem. Okay, so there on the basis of components we divide this subsystem. On the basis of component we divide this subsystem into four different categories. We divide this subsystem into four different categories. These are: first one, data path operators; second one is memory element; third one is control structure; and the fourth one is input output cells. Okay, what is it means? It means that if we want to design any processor, so in that processor we need various operators like AND gate, OR gate, subtraction operation, ANDing operation. So these operators are under the category of data path operators. Now the second part is memory element. It means that for designing of any processor we definitely require some memory elements. So these memory elements are in this category of memory elements. Okay, the third is control structure. Control structure means ALU, arithmetic and logical units. These arithmetic and logical units are under the category of control elements. And the fourth one is input output cells. Okay, so why we discussed these parts here? Because uh, because when any designer want to design any circuitry, then it has to follow some consideration also. Consideration also. It means that he tried to speed up its circuitry. He tried that his circuitry taking less space compared to some other circuitry, and it's the cost of its circuit is low compared to any other circuit. So all these are the consideration factor that the designer should follow while he design its circuitry. Okay, so in this unit first we discussed some operators. Okay, then later in the latter part of the unit, or in the fifth unit, we will discuss about memory elements, because these two elements are in your syllabus. Okay, so first we are moving towards the data path operators. Now first we are moving toward the data path operator. Now what is the mean of data path operator? We already discussed that data path operators are nothing but a operator that any processor is used while performing any operation. Okay, so for designing any operator, or for designing the circuitry of any operator, the designer should follow these steps, that is hierarchy, regularity, modularity, etc. Okay, these are the basic steps, these are the basic principle of design, these are the basic principle of design that any designer should follow. Okay, so here I am taking an example. So here I am taking a example of this circuit. So here I am taking an example of this circuit. So here I am taking an example of this circuit. This circuit is a this this A part is the broad way of the circuit. This A part is the summarized way of whole circuit. Okay, and the inner part of this circuit is represented in the B part. Inner part of this circuitry, inner part of this circuitry is represented in the B part. Okay, this block diagram or this circuitry is of the circuit of magnitude comparator. This circuitry is of magnitude comparator. We all know that what is the mean of magnitude comparator. We all discussed that what is the mean of magnitude comparator. Suppose I am taking 2 bits. Suppose I am taking 2 bit. Suppose I am taking 2 bit. Okay. Suppose I am taking 2 bit. One is a equals to 0 1 0, and b equals to 1 1 0. These are the 2 bits. Okay, and I want to check which one is greater, and I want to check which one is greater. At that time we provide these bits, at that time we provide these bit into a circuitry that check the magnitude of the circuitry. Magnitude means that check the bits of these inputs and find out which one is greater. Okay, so the circuitry that is used to find out which input is greater is known as magnitude comparator. Okay, so this one is the outer view. This one is the outer view of magnitude comparator. Here this a part represent the part represent the a input. This b part represent the interconnection from where we provide the second b input into the circuitry. Okay, this m represent the number of bit, because in a input we can say according to the circuitry or according to the requirement, there the value of m may be vary. Here we consider m is nothing but a value of input. M is nothing but a value of bit in any input. So in my example here, we consider the value of m equal to 3, because we consider 3 different bits. Okay, so when we provide these 3 bits into a circuitry, so according to the functionality of the circuit, according to the algorithm that is mentioned here, the circuit performs and provide the output which one is greater. Okay, here some algorithm is represented, that is less than or equals. Here you can see, here less than or equal to is given. It means that when we provide this value of a and this value of b into the circuitry, then first it provides the subtraction operation. And check the value of a is less than or equal to. If it is less than or equal to, if the value of it the if the output is less than or equal to which output, if a is less than or equal to b. If I am explaining again. Here we provide the value of a. From this port we provide the value of b into the subtractor circuit, and this subtractor circuit performs the operation of subtraction. And if the value of a is less than b or it is equals to b, then it provide the output value to this multiplexer. And if the value of b is greater than a, then it provide this value of it transfer the value into this operator. So here what operation is performed? Here various operators are connected. Here various operators are connected serially. Here various operators are connected serially, such as first one subtractor operator is connected, one equal operator is connected, one multiplexer operator is connected. It means that the operators are connected into serially. First one operator provide the output. If it fulfill the condition, then it directly provide the output. otherwise it relay the output into its neighbor operator to perform the circuitry and accordingly provide the output. Okay, I am explaining all this. I am explaining all this part. I am explaining all this part because I am explaining all this part because the second part, or we can say the inner part of the circuitry, represent that when we design any data path, है ना, before starting this data path operator, first we discuss about data path. So this two circuitry is only responsible to understand this data path. Now what is the mean of data path? The inner circuitry of the above diagram, the inner circuitry of this above diagram, the inner circuitry of this above diagram is represented here. The inner circuitry of this above diagram is represented here. Here you can say the first bit is provided, the a1 a2. The a1 a2 is provided into this port. The a1 b1 is provided into this port. The a2 b2 is provided into this port, and the a3 b3 is provided into this port. It means that while we design it means that while we design data path, or while we route the circuitry, so the connection will be such that the data flow is one side and the operator is connected into another side. You can easily understand by taking this metal. Here two metals layers are connected. One is represented this metal one. The vertical line is represented metal one, and the horizontal line represent the metal two. The vertical line represent the flow of data. Here you can say a naught, b naught, a1, b2, a2, b3. So this vertical line, this metal one, represent the flow of data, while this horizontal line or metal two represent the flow of operators. So one operator provide the output to the neighbor operator, neighbor output provide the output to the neighbor operator, neighbor output provide its neighbor operator. Okay, so the operator's direction is the horizontal, and the input data operator and the input data stream or the input bit operation is in the vertical side. Okay, so it is the first point that while it is the first point that while we design the data path operator or any of these operator, है ना, while we design data path operator or any of this circuit, first we have to frame the routing path. Okay, so while we design routing path, so always there is some regularity to represent the input stream and to represent the operators. Always we represent the input stream into one side and operator into another side. Okay, so these two diagrams is only responsible to understand the data path or the routing stream. I think you already clear all this part. Okay, now 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 we are moving towards the first data path operator. I think you can understand the difference between data path and data path operator. Data path is nothing but a routing. We use several algorithms, we use several schemes to represent the routing path. Why we use the algorithm to represent data path? Because we know that if we route the path of any circuit properly, then the area that is required to design any circuit will be less. Okay, so this data path routing will save the area. This data path routing will save the area that is required to implement the circuit. Okay, after study of this data path term, now we are moving towards the data path operators. Okay, first data operator is addition and subtraction. First data path operator is addition and subtraction. We already know that addition circuitry is used when we want to add two bit data. Suppose we have two numbers, one is a and another one is b. Suppose we have two numbers, one is A and another one is B, and we want to add two numbers and get output C. At that time we need a addition circuitry, है ना? And suppose we need to subtract two element, that is 1 and B. Suppose we need to do subtract two data, A and B. At that time we need to design the subtracted circuitry. Along with these operators, several else are there, such as multiplier circuitry, such as multiplexer circuitry, such as buffer circuitry, such as shifter circuitry. So all these circuitry, all these operators are under the category of data path operators. Okay, I think you understand it well. All these are under the category of data path operator. So in the data path operator, first we discuss about addition, then subtraction, then later on we will move towards the another circuitry that is in your syllabus. Okay, so first we will discuss the addition circuitry. We all know that there are the simply there are the two types of adders. One is known as half adder and another one is known as full adder. When there are only two inputs, at that time we need a half adder circuitry. In half adder circuitry we have two inputs and accordingly we have two outputs. What is the outputs there? Output is sum and carry. And when we have three different input, at that time we need to use full adder. Okay, so first we understand the basic part. Suppose I have considered a truth table of full adder. Okay, suppose I have considered a truth table of full adder. Here three here here three different bits are present. Here three different bits are present. One is A, another one is B, and the last one is C. Here three different bits are present. Okay, so by using these three bits, we will get the sum and we will get the carry. Okay, this one is the operation of simple full adder. In simple full adder, we add these three bits and accordingly we will get the sum and accordingly we will get the carry. Such as when we add 0 0 0, then we will get when we add 0 0 0, then we will get the sum as 0 and carry as 0. When we add 0 0 1, then we will get sum as 1 and carry as 0. Same as for the other input condition. Okay, so while designing or before designing any circuitry, first we have to make the truth table of any circuitry, you know. Okay, according to the truth table we get the output sum, we get the output table for sum as well as carry. So by using the Karnaugh map or any other operators or any other Boolean functions such as Boolean algorithm, we uh, we represent the Boolean expression such as sum equals to abc plus a b bar c bar plus a bar b bar c plus a bar b c bar. Okay, same as we will get the value of carry function also. Carry equals to ab plus bc plus ca. Okay, we can also factorize this carry term as ab plus c into a plus b. Okay, we can represent the carry term by using this expression, or we can use this below mentioned expression. Okay, why we change this carry expression into this term? Why we change this carry expression into this term? Because here we can say, when we design any circuitry, or when we design the circuitry in gate level, then by using the below one we need less number of operators as compared to the upper equation. Okay, so in the designing consideration, we should follow how we can change the expression. So we need the less number of operators to design the circuit. Okay, So this one is also a design considerations that always try to design any circuit, or always try to perform the operation by using less number of operators. So this will improve the area, or this will improve the speed of any operation. Okay. So this one is the equation of sum. So this one is the equation of sum. 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 This one is the represented by using this boolean logic function. We can while we designing gate level, first we have to find out the boolean expression. After it, first we have to find out the boolean expression. We already find out the boolean expression. In the later on, we have to design the circuit by using some gate level structure. We have to design the circuit by using some gate level structure. So we design this sum function. We design this sum function as, how can we design the sum function as, by taking this expression, by taking this expression. if we if we further solve this sum expression, if we solve this if we solve this sum expression further, then then we will get the expression for this sum expression as a XOR b XOR c. A XOR b XOR c. It means that if we use only two XOR operator, if we use only two or XOR operator, so we can, if we use only two XOR operator, so we can easily design the sum function. Okay, same as same as to design the carry function, same as to design the carry function, same as to design the carry function, we use the below mentioned gate structure. We use this below mentioned gate structure. And when we want to design this gate level structure, when we design this gate level structure using the transistor level, when we design this gate level structure using the transistor level, then the circuitry will look like this one. Then the circuitry will look like, then the circuitry will look like this one. This circuitry is the representation, this circuitry is the representation of the sum, is the representation of sum equation. And the below in the this circuitry, and the later on this circuitry, and this circuitry is the representation, this circuitry is the representation of this carry function. Okay. uh, here here you can see this a bar. Here you can say, here you can say a bar is represented as minus a. Here you can see the a bar is represented as minus a in the circuitry. Okay. So the place where minus c is written, you can understand by it by a bar or c bar or b bar. Okay. It is already mentioned here. Okay. So okay, now now what is the operation? If I trace this if I trace this CMOS circuitry, so if I trace this CMOS circuitry, so a bar is connected into this one. So here, from here we will get the a bar, and from here we will get the b bar. Here we will get the a bar, and here we will get the b bar. C bar is provided into this one, C bar into providers into this one. And we know that in the the P side, the upper side is the circuitry that is framed by using PMOS, and the below circuitry is the NMOS representation. And we know that while we design the CMOS circuitry, then it is the combination of PMOS and NMOS. Okay. So this one is the CMOS, this one is the PMOS representation, and its NMOS representation is represented here. Is its NMOS representation is represented here. Its NMOS representation is here. It, this one, and this one. These three NMOS is the identical form of this PMOS. Okay, this NMOS is the identical form of this PMOS, and these PMOS is the identical form of this NMOS. Okay, by using this PMOS and this NMOS, we design a equation, and by using these three PMOS and these three in NMOS, we design a circuitry. Such as here the output expression is, from here we will get A bar, B bar, so the expression will look like A bar dot B bar. The expression is look like A bar, the expression is look like A bar dot B bar. How we will get this expression? From this side, A bar dot B bar, and this one is the odd operation, so A bar B bar plus C bar, A bar B bar plus C bar. Okay, so we will get A bar B bar plus C bar from this side, and from this side we will get, this one is the B bar and this one is the A bar, this one is the B bar and this one is the A bar. So we will get A bar plus B bar, A bar plus B bar. From this side, we will get A bar plus B bar. Now this circuitry and this circuitry is connected in the parallel form, so the operator that lies between them is AND operator. So when we solve this circuitry, so we will get, when we solve this circuitry, so we will get this expression carry. Okay, so this one is the representation, so this one is the representation of carry circuitry, this one is the representation of sum circuitry, this one is the representation of carry circuitry, and this one is the representation of sum circuitry. Okay, and if any designer, because the design of because the CMOS design of any gate level design is vary according to the gate level circuitry. So according to designer, this CMOS circuitry should be vary. So if you are a designer and you don't want to use this XOR gate, you only want to design your some circuitry by using AND and OR gate combination, so you can use this circuitry. Here no XOR gate is used, here only AND gate and NOR gate is used for getting the combination of sum, and not OR gate as well as AND gate along with the NOT gate is used to find out the operation of carry. Okay, so you can also find out, you can also make the sum circuitry, as well as carry circuitry by using this gate level design. Okay, so the designing is not fixed, designing is not fixed, it is vary according to designer. You can use only one XOR operator, and you can replace another XOR operator by using some AND gate or OR gate. So this CMOS circuit, the design of CMOS circuitry will change. Okay, so according to designer, the CMOS circuitry is vary. The main consideration is that you always try to design by using less number of operator or less routing to minimize the area or to increase the speed of the operation. Okay, this one is the added operation, this one is the adding operation. Okay, now the next part is bit parallel adder. Now the next part is bit parallel adder. You study this topic in your digital electronic, where you study this topic in the terms of parallel adder, why we design the parallel adder. Parallel adder is a procedure where several AND gate operator where several adding operation is used to operate the adding operation parallelly. This type of operator speed up the process of adding. speed up the process of adding. So while so in the circuitry, in the designing of the circuitry, if speed is the main consideration while designing of any circuitry, if you are a designer and you need to design a circuitry for some third party, and the main consideration for the third party is the you need to speed up the circuitry. So at that time you should follow this type of parallel ladder, because when we design the circuitry by using the parallel ladder, at that time you will get the higher speed as compared to serial ladder. But the main drawback in parallel adder, the main drawback that occur in parallel adder is that, if the number of bit that you have to add is very less than the then there is very less effect in the output side. But if the number of bits are very much higher, suppose if here n is the number of bit, if the number of bit is very higher that you want to add in by using this parallel ladder, at that time the delay is very significant. The delay value is very significant. At that time you cannot use this type of parallel ladder circuitry. At that time you cannot use this type of parallel ladder circuitry. So at that time you need to find out some other way to speed up the process. So the next so that the next circuitry that you should follow for the replacement of this parallel adder is look ahead carry method. Look ahead carry method is also used for the addition purpose, but look ahead carry method provide the faster adding operation as compared to this parallel adding operation. Okay, here the circuit that represent the parallel adder implementation. Here the circuit that represent the parallel adder operation is represented. Here the circuitry that represent the parallel adder operation is represented. Okay, in here you can see the below adder is used to add the LSB only, and later on the next one is used to add its neighbor bit, and same as for the other also. Okay, so when we use this parallel adder, so all these bits are added parallelly, and you will get the sum faster than any serial adder. Okay, so if you want to increase the speed of this if you want to increase the speed of this parallel ladder, so there is some modification in the circuitry. If we do this type of modification, if you do this type of modification in your parallel ladder, so it will take less time as compared to the parallel ladder. If we add the not operator in every successive bits, if we add the not operation in every successive bit, and after the not operation, if you add the bit by using the addition circuitry, so it will provide the less time for the addition as compared to the simple parallel ladder. So this circuitry contain the less time as compared to the previous mentioned circuitry, because here some modification is done to speed up the process. Why we done this? Because in this time the designer main consideration is speed. The designer main concern is speed, so he want to design its a circuitry for the requirement of higher speed. So at the time you need to add these not gate for to speed up the process. If the designer main requirement is the area, at that time you cannot use this type of not gate in the circuitry, because you know that if you use this not gate, so because of this logic element along with the routing panels, the routing path will take the less space with the operator, so it takes larger area as compared to this simple circuitry. Okay, so according to the requirement, the designer will design the circuitry. This all part is mentioned in this theoretical part. Okay, this all part is mentioned in this theoretical part. Okay, suppose suppose the designer need adding as well as the subtracting operation in the same circuitry. Designer need the addition as well as the subtraction operation in the same circuitry. Now how can he do that? For this purpose, you know that you already study in your digital electronic that suppose you want to done the subtraction operation. So by using the not of operand and adding a one, or in other terms you can say by taking the two's complement of not opera by taking the two's complement of operand. Two's complement means, how can we calculate the two's complement? If we take the complement of the bit, and after taking the complement, if you add the one into it, then you will get the two's complement of the data. So for the subtraction of any circuit, you need to find out the two's complement of any data, two's complement of one bit, and add that bit to the first a bit, add that bit to the a bit here. One bit is a, you can easily understand it by taking this example. Suppose one bit is a and another bit is b. Okay, so what you will do, first you take the complement of this b bit. Okay, for taking the complement and for adding the one, you can use the XOR operator. If you take the complement of this bit by taking this not operator, and after the taking the complement, if you add the one, so these all operation can be done by using simple by taking simple one XORing it. It means that if you take the XORing of that second input, and after taking the XORing, if you add it with by adding operation, by adding the adder operator, then you will get the subtraction, then you will get the subtraction. So for the designing, so that we can say for the designing of subtraction circuit, by taking the same adding operator, you can implement it by using this circuitry. Okay, here you can say for taking the subtraction, first we have to find out the second complement or two's complement of second input, and after taking the two's complement, if we add it with the first input, then we will get the subtraction in the output side. Okay, so this one is the subtraction operator. So this one is the gate level design of any subtractor, and this one is the adder design, or the design that is used for the addition of any circuit. Okay, so the algorithm that I mentioned here, if first you have to find out the two's complement, then later on you have to add the one. These all is represented in these step 1, 2 and 3. You can easily go through this three steps and find out how can you calculate the value of subtraction. Okay, this later on the this circuit is the representation of sum and carry again. This circuit is the representation of sum and carry again. This one is the optimized circuitry. You don't need to mention all these other circuitry, because this all are the optimization of one into another. So you just need to remember that what is the mean of optimization. Optimization means that some modification in the circuitry to fulfill the consideration of the designer, to fulfill the requirement of the designer. It is the optimization. Okay, so okay, these all are the adding operation. These all are the adding and subtraction operation. So this one is the first operator. So this one is the first data path operator. And in next lecture we will discuss some other data path operator in our class. Okay, so thank you so much. I hope you understand it well. So mention your roll number with name in the chat box. Okay, thank you so much.